Hi, everybody. Welcome to Math with Ace, focusing on statistics today. We have been venturing into hypothesis testing. We're dealing with a single sample with either a parameter that is a mean or a proportion. So we're dealing with numerical data or categorical data. And in order to perform a hypothesis test, first of all, you have to set up your null and your alternative hypotheses. See a couple videos back. Then you need to check your conditions before you even start doing anything. Once you have set up your hypotheses based on the claim that you're testing, you've checked your conditions to make sure you should be running numbers, then you need to actually perform the calculations. And what we do is in hypothesis testing, we have this distribution that needs to be approximately normal because you're either dealing with a Z distribution for proportions or a T distribution for means. And in order to use a Z or a T distribution, you need it to have this bell-shaped curve. And so we have checked our conditions to verify that we can go ahead and use this type of distribution. But in our hypotheses, we are assuming some value to be true. This is your null hypotheses or null hypothesis. So it's either we are assuming some value about an average, or we are assuming some value about a proportion. So we're assuming that the average rate on a test or pass rate was a 75%, or we're assuming that 25% of the population wanted to rain today. But we have some sort of assumption about the population that we are then using to test our claim. And our claim is either going to be greater than or less than or different than. And so based on the claim, we need to calculate, using our sample data, we need to calculate the Z-score or the T-score and see where it lives. And then is it far enough away to be unusual? So in order to calculate our test statistic, we need some information. And remember, this is all based on, we're using sampling distributions to help us make these test statistics. For means, if that's your parameter, remember that's numerical data, or for proportions, and mean has mu as our population parameter that we're using. For proportions, we're using P as our population proportion. We are calculating a T statistic for means or a Z statistic for proportions, which is a Z-score or a T-score. And then we're finding out where that Z-score or T-score lives in our distribution, how far away it is from the null hypothesis, and then determining the likelihood of that happening randomly by chance. So the way that you calculate a test statistic, well, first of all, you're assuming some hypothesized value. So you have an assumption that is either mu sub 0 or P sub 0. That's your statement of equality in the null hypothesis. Then you collect a sample and you analyze the sample and get their summary statistics. So your sample data has an average and it has a standard deviation if you're dealing with means. So this is the sample average and sample standard deviation. For a proportion, you have a sample proportion. We also have a sample size for both. So in your sample data, you either get the average and the standard deviation, or you get the proportion depending on what type of problem you're dealing with. And then remember, for our sampling distributions, we're using our standard error because we have no idea about the population standard deviation for means. So that is where we take the standard error of X bar, which is the standard deviation of the sample divided by the square root of the sample size. We don't have an assumed standard deviation. We can't use that. For our proportions, we can use the hypothesized value here for our sampling distribution. So we take our hypothesized value in our test statistic. We are assuming that proportion to be true, and that's also how we calculate the standard deviation for proportions. Now we put all of that together. Remember, a z-score is the value that we have minus your hypothesized value divided by the standard deviation of the statistic. So our t-score here is going to be the x bar from the sample minus the hypothesized value from the null hypothesis divided by the standard error, which is the standard deviation of the sample divided by the square root of the sample size. That's our t-score. And remember, our degrees of freedom is n-1. For our z-score, we take our statistic, or point estimate, minus the hypothesized value divided by the standard deviation of the sampling distribution, which is the hypothesized value 1 minus the hypothesized value divided by the square root. And all of that is underneath the square root. So then what we do is we calculate that statistic, and then we use either a chart or technology to tell us how likely that is, assuming our null is true. So what you can do is, if you've done a normal, if you go to Stacklet and you do normal distributions and you enter in, if we're talking T and Z, 0 and 1, because we're assuming this is, your standard 0 or 1, and you have your t-score, you see how likely that is. And that is whether your claim is telling you which direction to deal with. So if your claim is a greater than, you need to be testing to the right of. If your claim is a less than, you need to be testing to the left of. And if your claim is different than, that's a pickle, because you actually have to determine, okay, if your z-score is positive or negative, you're going to do greater or less, and then you are, your p-value is doubled. So that's a whole situation. But what's happening here? Let's say I have a null hypothesis of equality, and then I have an alternative hypothesis of less than. So I have this assumed value here. Then I get my t-score, and my t-score is essentially, I'm trying to figure out how far away my sample data is. If my t-score is here, when my mean is 0, because I've now turned it into a standardized value. So I can do it like this. This is my t, or I have my hypothesized value and my sample data with all the other stuff in there, accounting for the standard deviation and whatnot. If it's pretty close, if your t-score is, 1 away or -1 away or something, that's not, the probability of that happening is pretty high. But the further away that you get from your hypothesized value, the smaller your probability is, because you're getting farther away from the mean. So remember, as you go, z-scores out, it becomes less and less likely. So let's say my t-scores over here, that's pretty rare. So what happens is you then go into your distribution. You either use your chart or you use formula, or you use technology, and you calculate the probability. And then that probability is how likely you are to have obtained the sample data you did, assuming that all is true. So we calculate this thing called a p-value. And the p-value is the probability of obtaining the sample data you did or data more extreme, because you can either be even smaller to the left or the right, assuming that the null is true. So let's think about this for a second. You are assuming some hypothesized value, either a hypothesized average or a hypothesized proportion. And then you calculate sample data, and then you calculate or you analyze your sample and get the data. And then you use that to calculate these statistics. And then you determine how likely it was to get the statistics. That's a probability. That is the probability of getting that value based on the sample data, assuming that the null is true, because it's all based on that. If you notice that 0 in there, it's all based on the hypothesized value. And so if your probability is very small, then that means it's very unlikely to have happened by chance, and that there is evidence that your null is off and your claim is true. Okay, so this is calculating a test statistic. Let's talk about making conclusions next.